Hello! In this teaching video we will go through the derivation of the Langmuir adsorption isotherm for the simple adsorption, single-site adsorption where no further reaction occurs during the adsorption. So we will consider the adsorption of substance M. The M can denote atoms or molecules, or in some cases even fragments of molecules. We will just think of M during this lecture. So that will adsorb on a surface which has some adsorption sites, and those are denoted with S in this video. All sites are equal. We are also thinking of a planar surface where, so that's the easiest way to think that the sites are equal. And once adsorption or attachment of substance M has occurred on the surface, these species do not interact with each other. This is a reversible process, as chemical reactions are, and the reaction equation concerning this case is substance M plus site S gives M dot S, so this means an unit of M adsorbed on an active site. And from the arrow you see this is a reversible reaction. It goes forward, we are attaching molecules or adsorbing, and reverse, we are detaching or desorbing molecules. We will also consider the site balance. So as depicted here, the number of sites is constant, the total number of sites. So we are denoting the total number of sites, CT, T stands for total, and some of the sites are vacant, and the concentration of those sites is denoted with CV, and some of the sites are occupied by our substance M, and the concentration of those sites is denoted Cm.S. And what are now the units of these concentrations? We don't need to care about that. In this lecture they just are the same units in each case. That can be mole base, that can be atoms per unit surface area, but they are in the same units. So we are going to derive the Langmuir adsorption isotherm, and this is actually the Langmuir type of reaction that we are going to derive it for. So it is adsorption where nothing else happens than the adsorption. So we are not releasing anything to the gas phase, and it's reversible, and the species don't interact with each other, and the surface sites are all the same. Langmuir adsorption isotherm, it's a model for a model case, but we are also measuring adsorption isotherms experimentally. And here I will just draw an example isotherm. So what we are interested in is the concentration of the amount of the adsorbed substance. So I denote it here with the CMS. It's the same one as here, as function of the partial pressure of M in the gas phase. And so these are things that one can experimentally measure, and the results can look something like this, or they can look different, but so typically the amount increases with partial pressure. So this would be increasing pressure. And because we are talking of chemical reactions which are typically reversible, you can also do this in the same measurement coming down with pressure, and I am just going to draw here some points, and this would be then decreasing pressure. In this case, you see that all these lines, all these points, they nicely fall in the same line. So this would be a case where there is no hysteresis, no difference between these two curves. In some cases there can be hysteresis observed. We do not consider that here in this lecture. So we want to have a model isotherm, Langmuir isotherm, to interpret those experimental results. How do we derive it? We will start considering the rates of reactions. So this isotherm, it is for equilibrium situation, so it's the concentration as function of partial pressure at equilibrium at a constant temperature. It's an isotherm, isothermal conditions. It's the same temperature throughout. There is no time included in the isotherm, but we will start deriving through considering time changes, rates of reactions. So first the rate of attachment and then the rate of detachment. Rate of attachment, we will call it R, small r, and rate of attachment of substance M. That, when we are considering this reaction, we can assume in the Langmuir adsorption model that these are elementary reactions. It means that the rate of reaction or rate of adsorption is dependent on the frequency of collisions between gas phase and the surface, and that is proportional to the partial pressure of the compound or the substance. Also, the rate of reaction or rate of adsorption is proportional to the amount of the other thing reacting. So in this case, vacant sites. So CV. And then there comes a proportionality constant. We call it the Km. This is the reaction rate constant, proportionality constant. So rate of adsorption, it's a constant times partial pressure of M times concentration of vacant sites. Sounds logical. Rate of detachment for a reversible reaction. That we need to consider also. I will call that R and denote it with minus M equals, again, a proportionality constant. We'll call it K minus M. And now we consider this to be an elementary reaction, so it's always proportional to the concentration of the reacting species. And now we need to consider that one, the concentration of the adsorbed species on the surface. So this would be CMS. Let us consider the ratio of these two. So we have the reaction here. I will mark it here. We have the K, M, the reaction rate constant for the forward reaction, and the K minus M for the backward reaction. So these are the ratio of these two is known as the equilibrium constant, and that is denoted typically with a large K. And then we will consider the net rate of the reaction, of the adsorption. And this will be, of course, the rate of attachment or adsorption subtracted with the rate of detachment. So we will call, let's call that net rate of adsorption. I will put there the ad. And this will be this term subtracted by that term. And what we actually want to do, we want to eventually come out with an equation where we have such terms that we can use them for analysis. We will use the equilibrium constant and get rid of the other proportionality constant. I will do it right away. So I will consider that minus that, and I will replace that one with small km divided by large Km. So it will be Km, so the proportionality constant, times the partial pressure, times the concentration of vacant sites. And then we have a minus sign, right? And then we wouldn't have the K minus 1, but we will replace that by K, small k divided by large K. I will put that large K here. And I will take care of this K by putting it to the front. And then what we have left is the pressure times CV. Partial pressure times concentration of vacant sites. No, CMS, I'm sorry. Concentration of occupied sites. So here we have the net rate of adsorption. Net rate of adsorption. We are talking of isotherms. They are measured for situations where there is no adsorption taking place. So the net rate of adsorption is 0 at equilibrium conditions. This is our key to getting to the isotherm, Langmuir isotherm, making the assumption that the net rate of adsorption is 0. Then what we want to do, we want to solve for the Cm.s from here. What we can do to simplify is that we have here a term that multiplies something and we are at 0, so this cancels out. And then we are going to solve for the Cm.s. I will write it here at the bottom. So Cm.s there is a PM that shouldn't be there. I need to get that out. That's okay. So that was of course related to the same mistake that I was going to put that one in the equation, but it was supposed to be that one, and then I put that PM and it's not belonging there. Let's take this one out. I'm sure that if you try this at home, you will also make similar mistakes. So let's just take this as a pedagogical example of deriving equations. So I will just multiply with Km, so that goes there, and change the sides, so we get the concentration that we are looking after. So the concentration of occupied sites occupied by M equals the equilibrium constant times partial pressure of M in the gas phase times the concentration of vacant sites. That looks already nice and simple, right? But it's not yet what we are looking for. We have there actually two things that we want to see something. We want to see concentration of the adsorbed species as function of partial pressure. But here we still have that amount of vacant sites which also depends on pressure. But what we didn't do yet is use the site balance. So we will replace this CV with the CV that we calculate from there. So CV, of course, is CT, number of total sites subtracted with an amount of occupied sites. So we will make that replacement. I will derive it still step by step. Cm.s equals, so the concentration of occupied sites equals the equilibrium constant times partial pressure in the gas phase at equilibrium times Ct, total amount of sites subtracted by the occupied sites. And now we just want to solve for this one. I will still do this step by step in a way. So if I'm going to multiply those two and then throw the term to the left side. So we will have, and then I will combine the terms. So we will have 1 times Cm plus, then what do we get from here? It's Cm times Km Pm, 1 plus the equilibrium constant times Pm times Cm dot S, concentration of occupied sites, equals, well, the equilibrium constant times partial pressure times the amount of total sites. Now I'm very close. I just want to throw that to the other side and solve for the concentration that I am interested in. Cm dot S equals Km, so equilibrium constant, times partial pressure in the gas phase, times Ct, so the total amount of sites, divided by 1 plus Km Pm. Here we have the Langmuir adsorption isotherm. This is what we were looking for. So we have an experimental isotherm, we have a model isotherm. Then, of course, what we can do is we can start analyzing the experimental data with the model. If we get a good fit, we can think that the assumptions that we made for deriving the model were perhaps correct. Perhaps the model describes reality. Perhaps not, we cannot be sure. If we cannot find a fit, then we can be sure that the model doesn't fit the reality. Some of you may have seen expressions of Langmuir adsorption isotherm, and you might not recognize this form. So what can still be done? We can present this in many ways. One way is to consider the ratio of occupied sites to the total sites. This is something that is known as coverage in chemisorption. So that is usually referred to with a theta letter. So ratio of occupied sites to the total sites, and if we throw that one over there, we get that theta equals Km Pm divided by 1 plus Km Pm. This might be the Langmuir adsorption isotherm that some are already familiar with. The derivation made here has been following largely the nomenclature of a book that we are following at Aalto University. It's by Scott Vogler, The Elements of Chemical Reaction Engineering. It's a very good book. I have also, in my earlier works, I have in a review article in 2005 also presented the Langmuir adsorption isotherm for atomic layer deposition. It is the same isotherm, but there it looks a tiny bit different. So I'm going to transform this one still to the form that is also in that article. So if you look at this equation, if you want to simplify it to the form 1 over something, what you can do is you can, of course, multiply by 1. So multiply with Km Pm divided by kmpm. This is fully okay, right? So what happens is that these terms cancel out. I will just do this. That leaves 1, and then that flips, and it's dividing this part. So we get to theta equals 1 over, and then we are dividing these parts with that one separately. So dividing kmpm gives by kmpm gives 1, plus then we are dividing 1 by that one. So this gives kmpm, taking the reciprocal of that. So this is also the Langmuir adsorption isotherm. All these expressions, they are the same fundamentally. It's just a little bit different mathematical way of showing that. So in the Langmuir adsorption isotherm, which is a model that describes the simplified reaction, assuming adsorption of a substance from the gas phase to the surface, where all sites are equal, where the adsorbing species do not interact with each other, so that this rate equation is valid. We have the constant times the pressure times the concentration. Then we get to the isotherm where the amount adsorbed, or the fraction of total sites covered, is a function of the equilibrium constant of the adsorption times the partial pressure of the substance in the gas phase. These are the only variables included. This is for the simple case of non-reactive adsorption. So one molecule or atom or something in the gas phase adsorbing as a whole to the site. Langmuir adsorption isotherm is not restricted to this simple case, but one can also consider the reaction of a substance from the gas phase with two sites at the same time, still with the assumption that the sites are equal. In that case, we would have dissociative adsorption. And it would be really nice to draw somewhere here, and I will do that. So now I need to clean. Let's see how I do that. Oh, no. Yeah. Okay. Let's see if anybody can see anything after this trial. Okay, I think I disappear. I will try everything that is available. Here we go. Some technical things still to improve, obviously. So it's my first trial with this Lightboard, and that doesn't remain unseen. Next time I'm gonna be a bit better prepared. And in a happy case, this is gonna be cut out of the video, but I don't know yet whether that will actually happen. But that would be very student friendly. Look at that, this starts to look like something. Here I see the camera light again. Yeah. Okay. So that's quite okay. So what we did now we derived the Langmuir isotherm, adsorption isotherm, for this simple case of non-dissociative adsorption on a site. You can also go through exactly the same type of derivation, thinking of a reaction with two sites. And there, the rate of adsorption, I will write it here, dissociative adsorption. Dissociative adsorption. So I would call this then M. Yeah. No, let's call that N, just for clarity, and we will clean that once more away. Yes. We'll call that N2 reacts with two sites, making two MS sites. And then the rate of adsorption would be equal to a proportionality constant times, again, the partial pressure of the N2, these would be molecules, obviously, in the gas phase, times the concentration of vacant sites to the power of 2. So this power to 2 comes from the fact that you would need two neighboring sites next to each other to be able to dissociate the molecule. That is along with the thinking that these would be elementary reactions. And then rate of desorption would be equal to proportionality constant times, again, the occupied sites to the power of 2, because you would need to have neighboring sites to create back the substance to desorb it. And I will not go through the derivation, but you can do it yourself if you want. And the resulting adsorption, Langmuir adsorption isotherm, would be very similar as that one, with the difference that this term comes as a square root. And still further, you can derive adsorption isotherms also for cases where you have multiple components adsorbing from the gas phase at the same time. So if we would have M and N substances which do not dissociate on the surface, and you would do the calculation, you would get so the same one plus, I hope you still see this, 1 times the adsorption equilibrium constant for this M substance plus the same, if I call that now P. No, P is for pressure. Let's call it R. Maybe that doesn't confuse in this example. Anyway, that is the other substance in the gas phase. So there are many model isotherms here. We have now derived gone through the derivation of the Langmuir adsorption isotherm. We did it for the simple case of just molecular or non-reactive adsorption on a single site, which is reversible. You can apply the same principles for more complex systems. You understand now that the Langmuir adsorption isotherm, it's a model. It is valid only for the case where the assumptions in the model are valid. It's not the only adsorption isotherm. There are many other model isotherms available that can be used to analyze more complex systems also. There are cases where one can perfectly fit data with Langmuir adsorption isotherms and extract meaningful equilibrium constants out of it. Also, what one can do is to measure the adsorption isotherms at different temperatures. So remember, adsorption isotherm, it's an isothermal system. You measure it at one temperature. These rate constants that we have here, the Km, K for the backward reaction, the equilibrium constant, they are constant when we are at one temperature, but when we are changing temperature, those also change. They have the exponential Arrhenius type of temperature dependency. So if you are measuring at different temperatures and extracting the equilibrium constant at different temperatures, then you can also access the internal parameters inside those constants. I hope that this has clarified the derivation and meaning of Langmuir adsorption isotherm for you. This is the first time ever I make such a teaching video at Aalto University for a course, and perhaps I will be making them in the future too, so you are most welcome to give feedback during the course feedback ways of how this was, whether it was useful, and suggestions for how to do things better, still better in the future. Thanks for watching.